Hi, I am Shaghayegh presenting on behalf of a team of Aalto University and Roohi Entertainment researchers. This paper is about predicting game level difficulty and churn. We present a model that is able to do that without players. We do this by testing the game using AI players and predicting human pass and churn rates from AI data. The AI model is tested and validated on a dataset of over 90,000 players and over 100 game levels. In an interactive game, it's impossible to predict all possible behaviors in advance. For example, players may invent new uses for game objects. In rocket jumping, for instance, players use the recoil of a weapon for locomotion. This unpredictability leads to an iterative process of prototyping and testing. Using human playtesters to test the game is time and money consuming, which is why playtesting using AI players is an active research topic. This paper utilizes a dataset of pass and churn rates from Angry Birds Relas. This data can be easily collected from all players. Pass rate is a measure of difficulty in the range of 0 to 1. 0 means that players never pass a level, and 1 means all players pass the level on first try. Churn rate is a measure of engagement, again in range of 0 to 1. At the first glance, the data shows that pass rate is a predictor of churn rate, but the relation is nonlinear and changes dynamically over the levels. Our paper proposes a simulation model that explains this. Several researchers have applied AI agents at their games to estimate the difficulty of game levels or detect design flaws. They usually exploit human data or heuristics to create human-like agents. However, we concentrate on deep reinforcement learning that doesn't need any hand-coded heuristics or human player data. Some work predicts an individual player's churn probability based on their in-game data. We focus on the prediction of average churn ratio per game level, not the probability that a particular player churns. Previous work has also investigated the relation of game challenge and engagement. For example, philosophy states that the balance between challenge and the skill needs to be optimized. On the other hand, Lomos found that in their educational game, lower challenge leads to higher player engagement. We model the relation between level pass and churn rates by combining deep reinforcement learning game playing agents and a simulation of how the player population evolves over the game levels, based on simulated skill, persistence, and boredom. Previous work has not investigated the combination of these two parts. Combining these components, our simulations produce human-like data where the relation of pass and churn rates changes correctly over game levels. Our game playing AI uses a standard deep reinforcement learning agent that is a neural network that outputs game actions based on the current observed game state. The agent interacts with the game through actions, in this case determining where to tap. This causes the agent to receive an observation of the resulting game state and a reward. The observation is fed through the neural network to determine the next action, and the learning process optimizes the neural network to output actions that yield high rewards. This is the trained neural network playing the game. We compare two models. In the baseline model, pass and churn rates are predicted through simple linear regression models, and AI gameplay statistics are used as the input features. Not surprisingly, this doesn't yield good results. However, we show that one can take the simple baseline pass rate predictor, normalize the predictions over all the levels to get a level difficulty measure, and then inject this to a simple population simulation block that determines which player churn. This then produces both more accurate churn and pass rate predictions and the population for the next level. This process is then repeated for the next levels. The player population simulation implements simple computational models of individual player differences. Each player in the population is defined as a tuple of attributes that determine the player's behavior based on simple rules. First, a player can pass the level if player's skill level is higher than the level difficulty. If the number of players' attempts to pass a level is higher than players' persistence, the player will churn. This way, we can model how less persistent players are likely to churn early. Even if a player passes a level, they may get bored and churn with some probability. This models how game engagement tends to decline over time. Furthermore, players can learn from their attempts to pass a level. Full details are provided in the paper. The population simulation is straightforward to implement as code. Numerical results on five-fold cross-validation show that our model acts similarly to the baseline model in terms of pass rate prediction. However, our extended model improves the churn rate prediction of the baseline model with an effect size of about 2 standard deviations. In summary, we propose a novel simulation approach for predicting churn and pass rates of game levels. At first, AI gameplay statistics are collected from each game level. The DRL agent only needs to be trained once per level. Level difficulties are estimated using these statistics. Based on the estimated level difficulties, the evolution of player population over levels are simulated. Our approach allows preliminary testing and validation of level designs without real players. Naturally, the model needs to be updated with real data whenever new levels are released to players. Thank you for your attention.